It's a great day for Gauss-Bonnet. It's Halloween. We got Murph back. In this video, we're going to briefly talk about how the genus of an orientable surface is related to the Euler characteristic. We're then going to use this to simplify an expression for the number of tetrahedra necessary to decompose a polyhedra. So we have a polyhedra. We wish to decompose it into tetrahedra, and we want bound on how many tetrahedra are going to be necessary. So we're going to use the Gauss-Bonnet theorem there. Murph's excited. Happy Halloween. Let's dig in. All right, welcome to It's a Great Day for Gauss-Bonnet, video 6. We're recording on Halloween here, so a little pumpkin to get in the mood. So last time we used the Gauss-Bonnet theorem to come up with a formula for the discrete curvature at a vertex on a triangulation. So recall we could come up with geodesic curvature, a formula for geodesic curvature. We're going to cut out a disk around the vertex, so we know we have Euler characteristic 1, and then applying the Gauss-Bonnet theorem gives us our formula for our discrete curvature. We then introduced a data structure to store triangulations, the half-edge data structure, and we talked about how we could use this idea of discrete curvature to remove vertices with zero curvature to reduce the size of our input to some algorithm. So we're not really speeding up the algorithm, we're just simplifying the input so that the algorithm runs faster. So that was last time. Feedback, well, starting to get some views, so that's exciting. We got our first like and our first subscriber, and it's amazing how motivating that is to me. So I know it's cliche, but like, comment, subscribe, it means a lot. All right, so our agenda for this video is we're going to talk about genus very briefly, and the fact that the Euler characteristic can be related to the genus via this formula. We'll give some intuition for that. And then we're going to talk about 3 papers of Bernard Chazal, and we're really going to focus on this last one where the Gauss-Bonnet theorem is used, and we're going to use the Gauss-Bonnet theorem to remove the genus from an algorithm. So here the Gauss-Bonnet theorem really is saying something about algorithms, which is my main interest of research, so I really like this. But we'll see what happened in these other 2 papers that kind of led up to this one as well. And so what are we doing? We're trying to decompose polyhedra into convex pieces using as few convex pieces as possible in some sense, or a small number, I guess I shouldn't say that. Okay, so let's talk about the genus of a surface. As usual, we're just given some intuition here. So you can think of a genus of a surface as the number of holes in the surface. So the sphere has genus 0. The torus has genus 1, and the 2-hole torus has genus 2, etc. And if we know our surface is orientable, well, then it's going to be homeomorphic to some surface or some n-hole torus or k-hole torus. So that's by the classification of surfaces, which is nice. So we haven't talked too much about orientable surfaces, but we do require our surfaces to be orientable, which means we have a way of defining a normal vector consistently. So when we compute curvature, we want to know it's signed, so we need to have a nice normal vector or a consistent way to define a normal vector. So if we have something like a Klein bottle, well, if we have a normal vector sticking out here, if we take some path around to the inside, our normal vector would be reversed. And so we don't want that to happen. So we have orientable surface here, and genus is the number of holes. And so if we have an orientable surface, we know it's some k-hole torus. So recall our Euler characteristic that when we defined it before was in terms of the number of vertices minus the number of edges plus the number of faces in some triangulation. Well, we can come up with a different characterization of the Euler characteristic, namely that it's 2 minus 2 times the genus. And these pictures hopefully give you some intuition for that. So if we start with a sphere, we can turn this into some sort of prism here by a homeomorphism. And then we're going to triangulate this thing. So I'm drawing these as smooth curves, but think of these as actually some sort of polygons, maybe with a lot of edges here. So then I'm going to bend this over. So we have this circle will become this circle, and this circle will become this circle. And we'll do that again. So I'm going to put another bend here. So this circle becomes the top here, and then this circle becomes this circle. And then we're going to drop our interior circle down a little bit, and then we'll see, so this circle becomes this circle. Still homeomorphic to the sphere, but now we're going to do something interesting. We are going to remove two faces, so f minus 2. So this face and this face are going to be removed, and we're going to join these two closed cycles together. So we're double counting. So we're going to remove one copy of each of these vertices and each of these edges. But notice that the number of vertices we remove is equal to the number of edges that we removed. So it doesn't change the Euler characteristic. So we're just subtracting two faces when we put this hole in it. And this takes us from the sphere to the torus. And so we decrease the Euler characteristic by 2. And so every time we could continue adding holes using this idea. And each time we do that, we'd remove two faces. And the Euler characteristic of the sphere was 2. So we're going to get this 2 minus 2g for our Euler characteristic. Okay, that'll be useful for us later. All right, so on to polyhedra. So here's our problem. We're given a polyhedra P, and we want to decompose it into a tetrahedra using few tetrahedra. So here are some examples of polyhedra. Well, this first, let's say this is forbidden. We cannot have these two a kiss at a vertex. So we'll say this can't happen. So at every vertex, we want to be able to iterate in a cycle around it. So if we have a surface, that's true. Okay, so in this first example, we could decompose this one into two tetrahedra, and that looks like the smallest number possible. Here we have a genus 1 surface. You could go through and, how many tetrahedra would we need? Well, you could start peeling them off, maybe have something like this and just keep removing. But the things can get complicated, so this is some sort of more involved genus 1 surface, and you want to decompose this into tetrahedra. It's not exactly clear what's the best way to do this. So we talked about triangulations of polygons before, so you can think of this as sort of a higher dimensional analog of triangulating a polygon, which we talked about in a previous video. Okay, you might say, well, that's what is the smallest number? Let's just decompose it into the smallest number possible. Well, it was shown that this is in fact NP hard. So unlikely there's any tractable algorithm to do this. So we're just looking for a small number, that would be good for us. Okay, so let's talk about some of Chazal's papers. So in 1984, he had a paper entitled Convex Partitions of Polyhedra. And here we're going to let n be the number of vertices and r the number of reflex edges. So So in a polygon in the plane, reflex edge is the interior angle is more than 180 degrees or pi. So in this picture, we'd have one reflex edge here, and we can kind of see that the angle inside here is, well, what are we doing? We're coming around here is, 4 pi over 3. So that's a reflex edge. And in this paper, he gives an algorithm that decomposes our polyhedra into approximately r squared over 2 convex pieces. And the thing we're interested in is this polyhedra he gives that gives a lower bound. So this thing is pretty cool. Here n is big O of the number of reflex vertices. And he proves that we need a quadratic in the reflex vertex number of convex parts. And so this is an interesting polyhedra here. So I kind of drew it that these look like they're straight across, but they're not. There's this sort of surface. They follow a curve here, and then the paper shows that you'll need a quadratic number. So this is pretty cool. I wanted to emphasize that. So that's sort of the first part of the story. Okay, so we have this polyhedra. Well, we need a quadratic number of convex parts in terms of the number of reflex edges. All right, and then let's move on to 1990, and we're going to talk about non-convex polytopes. And here the authors give an algorithm that decomposes a genus 0 surface, so think homeomorphic to the sphere, into big O of n plus r squared tetrahedra. So that's this is a pretty cool algorithm. It sort of takes off these caps and then constructs these walls. That's really clever. But they show, so for higher genus surfaces, the number of tetrahedron depends on the genus. So this is what we're going to use the Gauss-Bonnet theorem to remove this dependency on the genus. So we say, okay, so if we have a genus G surface, we can decompose it into n plus quantity r plus g squared tetrahedra. So very clever algorithm and a very well-written paper. Okay, so now we're moving along to 1995, and what we're going to do in this paper is, remove this dependency on the genus using the Gauss-Bonnet theorem. So first a lemma. In this lemma, we're going to say the number of reflex edges incident to V is at least the curvature of that vertex. And this is pretty clever argument. So what we're going to do is we're going to put the unit sphere around a vertex. So I'm considering this vertex here, and I'm going to project the surface onto the unit sphere, or consider the intersection. So here the intersection would look something like this. So we're going around and then down. So around and then down, something like that. Okay, and we'll let L be the length of this curve on the sphere. So we have great circles on the unit circle, or great arcs, pardon me, on the unit circle. So we can compute using the arc length. So arc length is the radius times the angle. So that tells us the length of our curve is just the sum of these angles here. So that's pretty cool. And then if we have no reflex vertices, then we have positive curvature. So the lemma is certainly true. 0 is bigger than negative positive value. And if we have some positive number of reflex vertices, what are we going to do? Well, we're going to bisect them. So this is going to go sort of behind, and we'll decompose this into r plus 1 regions. So I'm splitting the first one, and then I'll continue to split them. So we cut in half for each reflex vertex. And we'll end up with r plus 1 convex polygons on the sphere. So each one of those is at most 2 pi, because we're contained in a hemisphere here. And so we get that L is less than or equal to 2 pi. Oh, I'm switching to a capital R. I don't want to do that. Let's say this is lowercase r plus 1. Okay, so combining these things, what does this tell us? Well, we're going to have, let's stick with our orange for Halloween. So L is less than 2 pi quantity r plus 1. So we have 2 pi 1 minus kV is less than or equal to 2 pi quantity r plus 1. Dividing by 2 pi and subtracting 1, we'll get 1 minus kV is less than or equal to r plus 1, or negative kV is less than or equal to r, which proves the lemma. Let's put in our Bonnet macaque and a proof symbol. Uh-oh, what happened here? I gotta put him on this page. There he is. Okay, oh, I forgot to mention, in this paper, we're scaling curvature. So we're just dividing everything by 2 pi. So that might look a little different, but it's just a scaled value. Still valid definition of curvature. Okay, so what do we prove in the lemma? The lemma said the number of reflex edges incident to V is at least negative discrete curvature at V. So we're going to appeal to the Gauss-Bonnet theorem. Again, we did this scaling, so there's not going to be this 2 pi. I think we just divided everything by 2 pi in this version of the Gauss-Bonnet theorem. And we want to prove that any polyhedron of genus G must have at least G minus 1 reflex angles. So by our lemma, each vertex will appear in 2 reflex edges. So we get this quantity 2 here. And multiplying by the negatives, which is the sign of the inequality, or the direction of the inequality. And then we use our Gauss-Bonnet theorem. So this tells us that the Euler characteristic, so the sum, we're on a surface without boundary, triangulated, so this is the Euler characteristic of our surface, is greater than or equal to negative 2r. And as we talked about earlier, we can write this as 2 minus 2 times the genus is greater than or equal to negative 2r. Oh, I'm again switching back and forth between capitals. Let's make these lowercase. So r for reflex edges. And then just rearranging a little bit, what are we going to get here? We're going to get 2 minus 2r is greater than or equal to 2g. Is that what we want to? Nope, plus here. And dividing by 2, so 1 plus r is greater than or equal to the genus. So the number of reflex angles plus 1 must be greater than or equal to our genus. So we use, so this is where Gauss-Bonnet came in. So use Gauss-Bonnet. Okay, and what did that allow us to do? It allowed us to remove this genus from the number of tetrahedras. So we say, okay, we know that the genus is less than r plus 1, so we can replace this, and we get a simpler expression for the number of tetrahedra needed to decompose a polyhedra of genus G. So I think that is a very cool application of the Gauss-Bonnet theorem. Let's put our macaw in here because we proved something. Bonnet macaw, nice. Okay, so what do we do in this video? We talked about how the Euler characteristic can be expressed in terms of the genus, and then we use this to remove the genus from a bound on the number of tetrahedra needed to decompose a polyhedra. So I think that is just super cool application of the Gauss-Bonnet theorem. All right, happy Halloween. What are we going to do next time? I think we'll prove a discrete version of the theorem, perhaps. So tune in next time. Great day for Gauss-Bonnet. Happy